Okay, so last time we were uh, proving this theorem, proposition. Uh, U is an open and connected subset, and our aim is to show that U is arcwise connected. Okay. Uh, what we will do is the following. So let A be the following subset. It is the point of it is the set of points in U such that there is a path at gamma joining uh, x0 to x. Okay, so for any U in x, I'm sorry, for any x in U, if I can find a path joining these 2 points, what I mean by a path, of course, a continuous function defined on some interval, okay? So that one endpoint is mapped to x0 and the other endpoint of the interval is mapped to x. And A is the set of all points like this. So in other words, A is the subset of U which are connected to x0 by a path. Okay. Now, if I can show that A is equal to U, then of course, any 2 points here will be connected to uh, x0. But if any 2 points are connected to x0, then the composition of these 2 paths from x to y would give us a continuous path joining x to y. So let me write this. Note that it is enough to uh, show that uh, A is equal to U. Okay. All right. Let's do that. How I will show that A is equal to U? Well, to prove that A equals U, we will show that U is both is a non-empty is a non-empty subset of no, A is a non-empty subset of U, which is both open and closed. Okay, since U is connected, U is already connected. This would imply A equals U, because if you have a connected subset, or you may regard U as a connected metric space, okay, then the only subset of U which is both open and closed. Actually, the only subsets which are both open and closed are the empty sets and U itself. So if I show that A is also non-empty, then A had to be equal U. Okay. So A is already non-empty, right? X0 is in A because the constant path gamma, let's say from 0, 1 to U by gamma t equals x0, right? This is a continuous path. At both endpoints, it takes the value x0. Therefore, this is a path joining x0 to x0, joins x0 to x0. Therefore, x0 belongs to A, right? Remember, A is the set of points in U so that there is a path joining x0 to x. Uh, if I take the constant path joining x0 to x0, then that would imply x0 is equal to A. Alright, so A is in particular, A is not empty. Okay, A is not empty. Well, next we show that A is open. Alright, how can we show this? Well, let X is in A. How can you show something is open? Well, you have to draw a ball around this point which lies inside A, right? So let me draw first you a picture of what's going on. Okay, so let's say X is here and X belongs to A means there is a path joining X0 to X. And I want to show that there is a ball around X0 which lies in A. How can we show this? Well, you see, since U is open, there is a ball around X which lies inside U, right? So there is a ball like this which lies inside U. But, you know, this is just a ball. And any point in this ball, of course, is joined to the center by a straight line, right? If you take any point here, it is connected to the center of this ball by this straight line. But in this case, the point Y is just connected to the x0 by the composition of these two paths. First, I go by gamma and then by the line segment. Okay, the composition would be again a continuous path. So Y belongs to then A. Therefore, this whole ball belongs to A. So that's the proof. But let's write this down. Okay. So since U is open, there is some ball B X R for some R so that this ball BXR lies inside U. Okay. Let L uh, be this gadget from 0 to 1, 0 to 1 to U given by. So this is the line segment. Gamma t is what? This is 1 minus tx plus t times y. Okay. The line segment joining x to y. I can, of course, do all these because this is a subset U and U belongs to Rn. Therefore, there is a vector space structure in Rn. I can write such things, okay? You cannot do this in an arbitrary metric space, of course. Only works in Rn. Or, I mean, in a vector space, not necessarily Rn. Okay, so there is a path, let's call this L, joining X to Y. And this path, of course, okay, not gamma, this is L. Clearly, LT is always in B XR, so that it lies in U. Because any ball is convex. So balls are convex objects. In other words, if you pick 2 points in a ball, then the line segment joining these 2 points lies inside the ball. Okay. On the other hand, X is in A by the choice, right? We picked X in A, and it is in A means so that there is a path like this one, gamma, from, let's say, 0, 1 into U, so that gamma 0 is equal to x0 and gamma 1 is equal to x. So there's a path joining x0 to x and another path joining x to y. Now I'll take the composition of these two paths. Finally define the composition. We write it this way: gamma uh, uh, star L. This is a path from 0, 1 into x, not x, u, defined by this formula. Well, in one unit I moved from x0 to x, and in another one unit I moved from x to y. Now I have only 1 unit time, so I have to go twice as fast as as I moved in L and gamma. How I will do this? In the first half of the time, I'll go by gamma with twice the speed, okay? From 0 to 1 over 2, I'll go by gamma with twice speed, so I write 2t here. And in the remaining time, from t equals 1 over 2 to 1, I'll go with L, and here I will write 1 minus 2t, right? You see, this is continuous, because gamma and L are continuous, and the endpoint of the first one, so when you look at t equals 1 over 2, when you plug t equals 1 over 2, you get gamma 1. Gamma 1 is just x, and that is just L of 1, which is L of 1 not L of 0, which is 1 minus 2 times 1 over 2. Right. So at the end point, which is 1 over 2, this function and this function agrees, right? They are both equal to x. Therefore, this is continuous. And what is the value of this path at 0? When you plug 0, you get gamma 2 times 0, which is gamma 0. And this is x0. And at the other endpoint, when t equals 1, so you get what? L of 1 minus okay, I wrote this incorrectly. This is 2t minus 1. Okay, 2t minus 1. Alright, so this computation wouldn't change here. 2t minus 1. So I plug 2 times 1 minus 1, which is L1. L1 is just y. Right? So gamma 0 is this point, gamma 1 is this point, L0 is this point, and L1 is this point. The composition of these two paths would give us a path joining x0 to x, x0 to y. So, hence, this composition joins x0 to y, and thus y is in A. But you see, y was an arbitrary point, right? Y is an arbitrary point. Okay, so here this is an arbitrary point in this ball. This implies thus, therefore, this ball x r lies in A. Yes, so okay, I started with a point in A. I found some ball around A that lies inside A. Hence, A is open. Okay. All right. We also claim that A is closed. Why A is closed? Let's see. Okay. Actually, it is enough to show that. It is enough to show that U minus A is open, right? A is a subset of U, and if its complement is open, then of course A will be closed. Why this is true? Well, let's see. Here is my x0. To show that this set is open, I have to do what? I take a point here, take some x in u minus a. And then I have to do what? I have to find a ball around this, which lies again inside u minus a. A point is in u minus a means x cannot be joined to x0 by a path, right? This point is in u minus a, so it is not in a, means that there is no path joining x to x0. But in this case, if I take this ball as above, a ball which lies inside, uh, so this is xr. If I take this ball, no point in this ball can be joined to x0. Why is that? Because if a point, here, let's say y, can be joined to x0 by a path, then joining x and y again by a line segment would imply that x is joined to x0 by a continuous path. Therefore, we would end up with a contradiction. Hence, this y also cannot be joined to x0. So that's the proof, okay? So I start with x in u minus a. Uh, in other words, okay, uh, since u is open, there is some r positive, so that bxr lies inside u. Okay. Now, what I said, uh, then, okay, take any point, y in this ball. All right. If there were a path, gamma joining x0 to y, then uh, composing this gamma by the line segment L in this ball. Okay, this is the ball of radius r, joining uh, y to x. We would obtain a path joining x0 to x, a contradiction, right? Because we assume that x is not in A. In other words, there is no path joining x0 to x. Hence, y should be in x minus u. In other words, there is no path joining y to x0. Okay. So what we see is then any point in bxr, right? Any point in bxr lies here. This would show us what? So bxr lies inside u minus a, uh, and thus u minus a is open. And this is what we wanted to show, right? This means a is closed. Okay, so we showed that A is both open and connected and non-empty. Therefore, A is equal to U. So we have the following. Now U equals A, so that any point X in U is joined to X0 by a path, right? So here is X0. If I take any point, then this point can be joined by a path to gamma to X0. So if I take 2 points, then of course this point is also joined to X0 by a path. So composing these two paths, I find the path joining X to Y, and X and Y are just arbitrary 2 points. Therefore, U is path connected. Taking composition of paths as below, we see that U is path connected. So this finishes the proof, okay? This finishes the proof of the proposition. Okay. Any questions so far? Anything you don't understand in this proof? All right. So we proved what? We proved that an open and connected subset of Rn is actually path connected or arcwise connected. And the final thing I'll prove in this chapter is the topology sine curve is not path connected. So back to the topologist sine curve. Okay, what was this? So it's a subset of R2, and it has two pieces. One piece is this 0 comma y, y in R, and it has another piece which is x comma sine 1 over x. X is positive. All right. Okay, let's see how. Okay. So this has two pieces. Okay, let me draw. This is the x-axis. So this is one piece of the curve of the subset, and the other piece is this. Let me use a different color. As x gets larger and larger, sine 1 over x, 1 over x goes to 0, therefore sine will go to 0, but it is positive. So the graph gets asymptotically close to the x-axis, and as you approach toward origin, you get a sine curve with increasing frequency. So it gets up and down, okay, faster and faster, so that it goes up and down infinitely many times. Okay, this is the uh, object. So let me give names to these. Maybe I call this subset C. Okay, sorry. This is C, and this one is A, and this piece is B. Okay. All right. So maybe A, and this is B. All right. So we want to show that C is connected but not pathwise connected. Okay. C is connected first, but okay, not path connected. Let's see why this is true. For the connectedness, C is connected. We will proceed as follows. Well, A is connected, right? A is just a line segment. It is path connected. B is also path connected because any 2 points on B, right? If you take any points on B, there is this path joining these 2 points. So, and similarly, if I take any points, 2 points on A, they are connected by the line segment. Therefore, both A and B are path connected. Clearly, A and B are path connected so that they are connected. We know that any path connected subset is connected. But our aim is to show that C is connected. Now, C is A union B. But you see, if I take any point on, let's say, A between 1 and minus 1. So this point here, uh, you see that this point is, of course, 1, and this one is minus 1 because sine function goes up and down between 1 and minus 1. And you see, if I take a point like this, then if you draw a horizontal line, you get, points. Oops. This point, this point, this point, this point, and so on. You get infinity many points converging to this one, right? Let's say this is x0. I have this xn. Here, xn's are xn's belonging to B, and limit of xn is equal to x0, right? Just gets closer and closer to x0. Therefore, thus this x0 belongs to B closure because it's a sequence in B with limit x0. Well, this means what? This means B closure contains a point from A, right? Because x0 belongs to A and it belongs to B closure, uh, where B closure and A is not empty, right? But we know that since B is connected, right? If you have a connected set, then its closure is also connected. B closure is connected. Okay. Uh, and they contain, okay, so it's connected. And therefore, okay, yeah, do I want this? Wait a minute. Okay, so, hmm, okay, let me go like this. Yeah, okay, I'll go like this, where x0 is in A and in B closure. Uh, this implies C is connected. Why is that? You see, if I have a separation for C, so if C is like this, U union V, where both uh, U and V are uh, open, then uh, then since A and B are connected, we would have uh, A is in U or A is in V, and B is in U or B is in V, because otherwise A and so if some part of A is in U and some part of A would be in V, then A would be disconnected. Similarly, if some points of B lies in U and some points lies in V, then B would be disconnected. Of course, here I am assuming that these are open, where UV open and U intersection V is empty. Okay, so if UV is a separation for C, then since A and B are connected, uh, each A and B would be completely contained either in U or V. But suppose this is the case, A is in U. If A is in U, then of course x0 is in U. However, there is an uh, ball around this point, right? X0, and this ball lies inside U. But I know that there is this sequence xn converging to uh, x0, and xn is in B. Therefore, we would see that uh, and this would imply x0, sorry, U intersection B is not empty. But we know that B is in either U or V. Okay. So if B contains some points from U, then we would have that B is in U, so that B is also in U. So what we see is then both A and B are in U. Hence C, which is A union B, is in U, and this implies that so that U C is connected, right? Why is that? Because whenever I take two open sets covering C, which are disjoint, then C lies completely inside one of them. Okay. This means that you cannot separate C by two disjoint open sets. Therefore, C is connected. All right. All right. Let me stop at this point since it is 9:30 already. In the second hour, I'll finish this proof. So in the second hour, uh, I'll finish this. Is not path connected. Okay. Let me stop here.